Hello everyone, my name is Edward Eaton. I'm a PhD student at the University of Waterloo, and today I'm very happy to be talking to you about a paper I wrote along with Fang Song called A Note on the Instantiability of the Quantum Random Oracle. So this is a paper that's about the various models that we do proofs in and the relationships between those models. So I thought I'd start with just a brief note on the random oracle model, although I'm sure we're all very familiar with it. So in the random oracle model, all queries to various hash functions are managed in some sort of special way in the proof. This is done in order to extract additional information from the adversary, program certain points, and guarantee that information is unknown to the adversary, depending on the proof. And this is often constructed through some sort of lazy sampling method where anytime a query comes in from the adversary, a new uniformly random output is sampled and then added to some sort of table that's maintained for consistency. So in 2011, it was realized that we might want something stronger than the random oracle model, and in particular, the quantum random oracle model became defined. The idea here is that because an adversary with a quantum computer can potentially run a hash function in superposition, they should have access to a random oracle in superposition. So we can define our the interaction with the quantum random oracle in sort of a similar way, but here we have a superposition of inputs, and this maps to a superposition of those same inputs with an output register XORed with the output of the hash function. And it's kind of constructed like this just to make sure that the overall transformation is invertible, a requirement for quantum computing. And constructing a proof in this model is quite a bit more difficult because of the now new quantum access. So in the past 10 years or so, we've seen a lot of papers that have tried to develop new methods to manage the oracles and establish various proofs in this model. Finally, we have the standard model, which is simply where the adversary is given a complete description of the hash function, and we really don't concern ourselves what they do with that description. They can run it honestly, they can run it partially, whatever they want to do. And this corresponds to the real world. In the real world, we don't know what the adversary is doing with the code that runs a hash function. It's up to them. So pretty much since these models have become defined, people have been interested in the relationships between them. And it's fairly easy to see that security in the standard model implies security in the quantum random oracle model, which implies security in the random oracle model. So there's a bit of a hierarchy here. We can see that, if you have a proof in the quantum random oracle model, then by considering an adversary that only queries the quantum random oracle classically, that immediately implies security in the random oracle model. And similarly, if you have a proof in the standard model, then because you don't even need to maintain a random oracle, that immediately implies security in any other random oracle model. But people have been interested in the reverse direction. Is it possible that security in the quantum random oracle model could imply security in the standard model? Probably not, but people have been curious about, if there is a separation, what does that separation actually look like? And what can it tell us about when we do proofs in one of these lower models, like the random oracle model? What do we have to watch out for to make sure that this doesn't result in a break in the standard model security? So one of the earliest papers looking at this was by Kennedy, Goldreich, and Levy in 2004, where they established a signature scheme secure in the random oracle model, but insecure in the standard model, showing that that's impossible. But since 2011, the position of the quantum random oracle model in this hierarchy has not been as clearly defined. So there's kind of some questions here that have now recently been resolved. So earlier this year, Yamakawa and Jandry established a scheme that was secure in the random oracle model, but insecure in the quantum random oracle model. And the discussion of today's talk is about the separation between the quantum random oracle model and the standard model. And in fact, we will show that, unsurprisingly, quantum random oracle model security does not imply standard model security. So our contributions, We analyze various separations that are between the random oracle model and the standard model, and we show how the proofs of these constructions can be elevated and actually modified to work in the quantum random oracle model so that we can show a separation between the quantum random oracle model and the standard model. So specifically, we elevate the separation from CGHO4 from the random oracle model to the quantum random oracle model to establish the separation. And then we also re-examine another separation by Moore, Renner, and Holenstein from 2004 as well, and show that the original proof actually doesn't even need to be modified, and it still works in the quantum random oracle model. And finally, both of these separations have sort of a small gap in that they only apply to signature schemes that sign very long messages. And so we elevate proofs from another paper by Kennedy, Goldreich, and Halevi, this one from just like a year later, that considers signatures on short messages and shows that you still have a separation there, and we elevate those results from the random oracle model to the quantum random oracle model. So in general, to establish a separation between two models, say you want to show that security model A does not imply security model B, you need to construct some protocol. For us, we'll be using signature schemes, show that it is secure in model A, and show that it is insecure in model B. So for example, the CGHO4 paper says they show a signature scheme that is secure in the random oracle model, but insecure when that oracle is instantiated with any real-world hash function. So to establish a separation, we need, so we're constructing a signature scheme secure in one model but insecure in another, and this is generally done by starting with a signature scheme that is totally secure in model A, and modify it so that it interprets all incoming messages to be signed as a proof that we are in model B. And if the proof rejects, then you simply sign the message normally with sigma and return the signature. However, if the proof actually accepts, so the incoming messages is a proof that you are in model B, then you return the secret key. So in model A, we start with a scheme that's secure in model A, and any proof that we are in model B should be rejected because we're not in model B. So the scheme sigma is basically unchanged, and since sigma is secure in model A, this should remain secure. However, in model B, it should be easy to construct a proof that you're in model B if you're in it, and then you can just submit such a proof in a chosen message attack, and the secret key will be recovered. So it is trivially insecure in model B. So a lot of the work ends up being to show that it is still secure in model A when you make these modifications. So say model A is the random oracle model, and model B is the standard model, and the hash function used is SHA-256. So standard model, but only with SHA-256. So your proof, for example, that you're in model B, the standard model, could be simply a check to see whether h of m is equal to SHA-256 of m. Now h of m here is the function that if you're in model A, the random oracle model, that's going to be the random oracle, but if you are in model B, then h will be replaced with SHA-256. So in the random oracle model, the probability of these things colliding on any given input is negligible, and so the task of trying to search for an input where they match is a not feasible one. But in model B, h is going to be replaced with SHA-256, and so it's trivial to do for any m. But the more interesting question here is, can we do this when we don't know what the hash function used in the standard model is actually going to be? This is what Kennedy, Goldreich, and Halevi set out to answer in 2004. So we want a proof system that is going to reject whenever h is a true random oracle, but can be made to accept when h is instantiated with any hash function. So how can we do that? We can call this a proof of non-randomness, a proof that the oracle that we're interacting with is not actually truly random. So how can we prove that a function isn't random? Well, a complete description of an actual truly random function, like a random oracle, let's say from n bits to n bits, takes an exponential number of bits to describe, because it has to be described for every single input if it's truly random. But descriptions of real-world hash functions are generally not exponential in size. They're just a reasonably sized amount of code. So a small description of a hash function that matches some function h on many, many inputs proves that h is not a random oracle, so long as these inputs are sort of determined in some sort of random way. Okay, so this gives us our first idea for constructing a scheme that is secure in the random oracle model, but insecure in the standard model. So you start with a scheme secure in the random oracle model, and then when you sign a message, you interpret that message as a description of a hash function, hm. Then you check to see if h of m, here this h corresponds to the random oracle, if you're in the random oracle model, matches with hm of m. And if so, return the secret key. Otherwise, you sign the message normally. But there's a problem with this method. Executing arbitrary code submitted by the adversary means that our signature scheme is no longer guaranteed to be polynomial time. So the solution to this was to use something called computationally sound proofs. This comes from Macaulay in 2000. So as a brief description of computationally sound proofs, this is a proof methodology so that given a function f and an input x, you can construct a proof pi such that f of x is equal to y, such that generating pi takes time polynomial in the time to run f, but the length of pi is polylogarithmic in the time to run f, and the time to verify pi is polylogarithmic in the time to run f. So pi is relatively short-ish in the runtime of f, and the time to verify it is short. So this means that now on input of a message m, this is the signature scheme we're going to use to separate these. So on input of a message m, parse out that message m as a pair f and pi, and then check run the CS proof verification scheme to check if pi is a proof that f of m is equal to h of m. And if so, return sk. Otherwise, you just sign m normally and return the signature. The scheme is now guaranteed to be polynomial time. But note that it's still challenging if you're in the truly random oracle to find a position where these two things should match, because here m actually contains partially a description of f. So we want to extend this to the quantum random oracle model so that we can show that this scheme also is secure in the quantum random oracle model and establishes a separation between the standard model and the QROM. It's obviously insecure in the standard model because you can generate proofs for any instantiated hash function quite easily, just by running the CS proof scheme with that hash function. So is the scheme also secure in the quantum random oracle model? So the security of CS proofs, which are an important building block of this scheme, was not proven until recently. But last year, in a paper by Chiasé, Manahar, and Spooner, they showed the quantum random oracle model security, and you have a link to the paper there. This relies on the compressed oracle technique that was recently introduced by Jandry in a 2018 paper, and is a really interesting new technique for use with quantum random oracles. So the security of CS proofs is one part of the security of the signature scheme, but it's not the entire thing, so we also have to consider the general security of the construction. So this is the theorem that we ended up proving in our paper. So we considered G a sort of random function that outputs a single bit, such that there's basically a negligible fraction of the domain here returns 1. Then you consider a quantum adversary capable of breaking the existential unforgeability of this signature scheme with probability p in the quantum random oracle model. And then we show a reduction algorithm that is capable of either breaking the underlying signature scheme, breaking the computational soundness of the CS proof system, or finding an input x such that g of x is equal to 1. So, as mentioned, we're going to use a quantum accessible oracle G that is marked on a negligible fraction of inputs. And we'll construct a quantum random oracle H so that these inputs are exactly the ones where h of m matches the value produced by parsing m to f and pi and computing f of m. So now a valid proof that f of m is equal to h of m now means that either this, in the case that this isn't true, that f of m is not actually equal to h of m, then the adversary managed to create a proof of a false fact. and therefore CS proofs have been broken. Or alternatively, the adversary was able to find an M such that these actually do match, but this only occurs on the points where G is marked, which should not be able to be done by the optimality of Grover's. So that establishes that separation, at least with that methodology. But as mentioned, we also wanted to look at another scheme that considered only signing short messages. So the proofs pi involved in the CS proofs are fairly long, and this leaves open the possibility that the quantum random oracle model security implies standard model security if the scheme is restricted to signing just very short messages. So to ensure that this is not the case, on another paper from Kennedy, Goldreich, and Levy, they showed a signature scheme that is secure in the random oracle model, but insecure in the standard model, but this scheme only actually needs to sign short messages. The basic idea is that we're still going to have a proof pi of non-randomness, but rather than sort of sending over this proof pi all in one go, we're going to feed this proof to the signer one chunk at a time. And when this proof completes, then the signer will return the secret key. But there's an obvious problem with that, which is that in general, signing should be a stateless process. So this doesn't really match our description of a signature scheme, unless you're using something like LMS or XMSS. But we want to prove this for stateless signature schemes. So we need a way to feed this proof pi one chunk at a time that doesn't actually require the signer to maintain any state. So the solution to that is to feed the internal state of the verifier back to the adversary as part of a signature, so that the state can be maintained. And then when the next chunk of pi is fed to the verifier, include the previous state. As long as the internal state isn't too large, the messages can remain small. However, there's an obvious problem here, which is how do we know that the adversary isn't messing with these intermediate internal states? But for that, we can use a simple macking sort of procedure, a symmetric authentication scheme to make sure that this doesn't change over time. So to show that this scheme is also secure in the quantum random oracle model, we needed to elevate several lemmas to the QROM and change some of the proof techniques just to simplify them and clean up the process in the QROM. This is the theorem that we eventually arrived at. So we consider, again, a quantum adversary capable of breaking the existential unforgeability with some probability in the quantum random oracle model. And then we establish a reduction algorithm that, with high probability, is capable of either breaking the underlying signature scheme or finding a collision in a random oracle. So similar to the previous scheme, if the adversary wants to win, they have to be able to create a false proof in order to trick the signer. So, however, the proof here, rather than CS proofs aren't used for this scheme. Instead, the proof is actually going to be the process of the signer honestly executing the function in rounds. So state is going to be carried over by an authentication tag, as mentioned. So the adversary either has to forge a new authentication tag or find a new state for which an old tag is valid. The first case corresponds to breaking the second preimage resistance of the scheme, whereas the second case corresponds to breaking the collision resistance of the oracle. So in full, we consider a function g1 that is marked on one position and a function g0 that is not marked at all. And we're going to reduce the security of this scheme to distinguishing between the two. So we construct our macking oracle by having an oracle O that on input message and the authentication key, in the case that GB of AK is equal to 0, we return O0 of message AK. GB here, so we're reducing to distinguishing between the two, so we have access to one, but we're not sure which, so we'll just call it GB. And if GB of the AK input is equal to 0, then we use this O0 on the message and the authentication key. Otherwise, if GB of AK is 1, so if you've found the one marked item and B is equal to 1, then we return O1 of the message. This means that we can issue tags using O1 when as the signer we need to issue a tag. And if G1 is actually used, then the tags will be valid, with the authentication tag being exactly the authentication key that is marked, which we'll call X. This allows us to issue valid tags without even knowing what the authentication key is. However, if G0 is used, then tags will be totally disconnected from O, so the success probability is actually negligible. If these two cases are distinguishable, then this means that G0 and G1 can be distinguished. So that is a rough outline of the proof, establishing that these schemes are all secure. Obviously, there's a lot more details, especially with regards to some of the quantum aspects of this. But of course, there's kind of still an underlying question of how should these results actually be interpreted? What do these actually mean? What does the existence of such a separation mean? So in the original CGH paper, they argued that, this potentially means that the random oracle model shouldn't actually be necessarily trusted as a proof model because it doesn't imply security in the real world, and there are examples of schemes for which you can prove the random oracle model security, but the scheme in the real world is insecure. However, this is not a universally held opinion. For example, in a paper by Koblitz and Menezes from 2015 called A 20-Year Retrospective of the Random Oracle Model, they argued that in practice, the random oracle model has not really led to any concrete security failings, but that in fact, people's attempts to avoid the random oracle model and adding additional complications into their schemes have actually led to some problems and have led to more complicated schemes that do not necessarily provide better real-world security. So our interpretation of these results is something more like, this appears to show that the quantum random oracle model appears to be on similar footing to the random oracle model, at least in its relationship to the standard model. These same separations work between the two. After seeing this talk, I think, depending on your feelings coming into it, you might actually conclude from the talk that proofs should be in the standard model. You could argue that QROM security cannot imply standard model security, and therefore you should aim for the most realistic model possible, the strongest model possible. But you may also decide that proofs should be in the quantum random oracle model, because after all, it's more realistic than the ROM, but still allows most proof techniques that the standard model cannot provide. You may even decide that proofs should be in the random oracle model. After all, the proofs and the schemes are simpler when they're in the random oracle model, and the relationship between the QROM and the ROM to the standard model is actually the same. There's no real right answer here. These are all totally valid kind of things you could conclude, and I think it just depends on the scheme that you're constructing and what you feel is the best way to construct the best scheme with the best proof, which context is matters a lot in that situation. Thank you very much for listening to my talk. And again, if you want to read the full paper, you can find it on ePrint. Thank you.